in this case, is the centripetal force. So, center seeking. I feel like I've done this with this one. Still no. Okay. Now, I pronounce it centripetal. I've talked to other physicists where I've mentioned centripetal, and they kept hearing me say centrifugal because the pattern is the same, they sound very similar. This is, some will overemphasize and call it centripetal, which also I think might be the British pronunciation. It's a little bit clearer than that other word, centrifugal. So let's talk about what that is. Center. Mean. So what word do we have in English that uses this and that has something to do with fleeing? Yes. PET. What word do we have with PET in it, which talks about going towards each other? Yeah, that one's harder to see. Competition. All right. This is the word, when people use this word down here, they usually mean centripetal or centripetal. There is a proper way to use this, however, most people do not use it correctly. Therefore, we will not talk about this. I don't even want to say the word because I want you to sort of cast it from your mind, because 99% of the time when people use it, they use it wrong. So centripetal is what usually should be said. Centrifuge, most of you have dealt with a centrifuge at this point? I'm trying to think of, no? Okay, do you know what a centrifuge is? You take, it's something that spins, you put liquid in, like blood into it, and you spin it around and the blood separates into parts based upon the density. All right, that's a centrifuge. It really should be called a centripete in my opinion. However, I was not asked and we're stuck with the name. All right, and potentially we will never use that word again. Centripetal is this force that's pulling towards the center. Centripetal acceleration is the acceleration towards the center. And I know what you're thinking. Hey, all that's great, but could we do a problem with it? Yes, we can. So let's set up a nice scenario here of I have a table. With a hole in the middle, so this is a side view. I got a mass hanging down here. Got a mass up here. This is all that A and B. From an overhead point of view, I've got a table. I got a hole in the middle. I have mass B here, or let's stay over here. I have mass B here, and mass B is swinging around in a circle. We're going to make this a little bit nicer, and the table on top is frictionless. The rope is ideal, and the rope is close enough to parallel to the table. Mass of A will make 2 kilograms. The mass of B will make 0.5 kilograms. So if I just set this up, so I got a 2 kilogram mass hanging below and I got a 0.5 kilogram mass there. If it's just sitting there and I let go, what's going to happen? Think about when you did the Newton's law. If you had 2 kilograms hanging off the end and only a half kilogram up on the table, what would happen when you let go?
The heavier one's going to go
I would hope so. Otherwise, physicists have been lying to me. So that would fall, this would go, get sucked in towards the hole. However, if B is spinning, we can keep A from falling. So let's take a look at that. And I did put it away. So let's take a look at, from the side view, what are the forces acting on B and what are the forces acting on A?
A is weight. Tension.
We're done with it. What about B?
Normal. Tension. Weight.
Are you stopping there? You're not sure?
I think so.
Cassandra says you're stopping. All right. All right, that's it. We got the two forces right there. In this scenario, A is going to be in equilibrium. Static equilibrium. Equilibrium says that the velocity won't change. Static means it's at rest. The other type of equilibrium is called dynamic. If it's moving and in equilibrium, it's dynamic equilibrium. So B is not coming off the table or digging into the table. These are going to balance each other out. But I do have an unbalanced force here. There is a net force acting on B. There's no way I'm going to add those three forces together and have it come out to zero. So it is unbalanced. Matter of fact, that tension right there is pointing towards the center. As B is spinning around the circle, that tension is always pointing towards the center. Which means that's the centripetal force. A is in equilibrium, so I know those have to balance each other out. So my tension is equal to my weight of A. What's the formula for weight?
M times G.
And my tension from this up here is equal to mass times my centripetal acceleration. Put a little c there for centripetal. That's mass of B. So that's mass of B times v squared over r. So I do need to get that bit of information. R is the radius of the circle. And let's just make that, what number am I? Let's say I'm using 2.5. We'll make that 3 meters. It's a really big table. The radius is the size, the height of the room. Let's plug in numbers. I know that the tension, based because A is right there, is going to be its mass, 2 kilograms, times G. And let's put this on Earth too, where G is 10 meters per second squared. So what is G? Oh, sorry, what is the tension? Come on.
20 kilograms per meters per second squared.
1 to any first.
Yeah, I didn't mean to say the first part.
Okay. If you remove the first per kilogram, meters per second squared, otherwise known as? Yes. 20 newtons. That 20 newtons here is equal to the mass of B, which is 0.5 kilograms, times the speed squared divided by how far the radius of that circle, which I established as 3 meters. I'm trying to solve for V, so the math problem I'm working on here. $20 is equal to 0.5 V squared over 3. That's the math problem we're working on. So how do you solve for V?
You multiply times that.
What'd you say?
You're looking for change of velocity.
I'm looking for speed.
Oh. Multiply by 3 on both sides.
Yes, all right, so we first need to isolate V squared by getting rid of this other, the riffraff here. So multiply by 3, since we're dividing, we need to get rid of it by multiplying, so I have 60 is equal to 0.5 V squared.
Divided by 0.5.
All right, now since they're multiplying here, we have to undo that, so we divide by it. So I get 120 is equal to V squared.
Square.
And now I need to get rid of the squared by square rooting. And so V is equal to 10.9 something. Units?
Meter per second.
So that's how fast, as long as that V is traveling at 10.9 meters per second, then A will be in equilibrium. So now, now, we don't have a frictionless stable. Oh, yes, private.
Does the centrifugal force only have to do with tension?
No, just in this case. You ever seen at least ads for it in a circus where you got the motorcycle zipping around the cage?
Yeah.
And in that case, it's the normal force, or part of the normal force that's creating the centrifugal force.
Okay.
If you're driving around a curve on a banked road, the normal force is pointing this way, it's banked, and it's the horizontal piece of it that's supplying the centrifugal force in that case. All right, so as I swing this around, I'm holding on to the bottom of it. So let's stick a mass on there. Put a 200-gram mass. Now I want to swing it so that this does not move up and down. I want it to be in equilibrium. Now if I spin much faster, this is going to start to rise. Now it might not be easy to see that this moved up, so that's why the tape is here. The tape, it's much easier to see that distance. Stop swinging. It's much easier to look at that distance, so I was keeping my eye on this. There's also a mark on the string here that helps. I want the bottom part of that mark to be at the bottom of the tube. And so I want to swing this, and I can then time how long it takes to go around 10 times, so I know the time it takes to go around once. So if I timed it, let's just say it takes 6.37 seconds. I did something similar earlier today, and it was somewhere around there. So if the time for 10 revolutions was 6.37 seconds, what is the time for 1 revolution? Or how would you find it?
6.37.
Yes, just 0.637 seconds. That's also, since that's for 1 revolution, that's called the period, capital T. That's not a torque symbol, that's essentially a capital T. And the radius the distance from the top of the tube to the center of mass. So when that mark is there, that distance right there, I measured earlier, is 70 centimeters. So I have this thing traveling in a circle with a radius of 70 centimeters. It takes that long to go around once. We can figure out how fast it's moving. We can figure out speed. So how do you find speed?
Omega.
Don't want to use the omega formula. So it is equal to omega r, but looking for more of the classic. Think about the units. If you're driving down the highway, what are the units? Okay. Miles are units of?
Isn't it G times D?
That's a specific case of an object falling. Looking for something more general.
You're not looking for B average.
Maybe, depends on which formula you're about to pull up.
It says speed initial, says D.
That assumes acceleration is constant, and acceleration is constantly changing directions here. Let's go back to units of miles per hour. Miles are units of what?
Distance.
Distance, and
Times time. Distance divided by time.
yeah, it's distance over time. While I have my time, it's the period. What about the distance it's traveling in one period? Traveling in a circle, what is that distance called?
Circumference.
And the formula? There's two circle formulas that most people know.
2 pi radius squared.
I don't know if everyone said this, but I definitely heard someone say it, 2 pi r. So I can find the speed of this just by 2 times pi times r, 0.7 meters, divided by the period, which is 0.637 seconds. And I get the speed, which is somewhere around 7 meters per second. A little bit less, so 6.98 meters per second. I'm doing this in my head, so if someone uses a calculator, they can tell us what the real answer is. Tension mounts, it's getting exciting.
I don't know where pi is on the calculator.
Just use 3.14159.
What was it, 3.1?
159 is on a diagonal, which helps me.
6.904.
904. All right, that's how fast it's going. The mass that I had hanging down below was 200 grams. So I know that my tension, so my weight of this is 0.2 times 9.798 meters per second squared. That's got to be equal to my tension because A was not moving up and down, I hope. Just for the sake of this, I'm going to make this 10.
Where'd you get 0.2 again?
That's the mass. It's a.
Oh, okay.
I was trusting the manufacturer for this. So this is about 2 newtons. The tension is equal to, therefore, equal to 2 newtons, basically from this right here. So I have 2 newtons is equal to, plugging into this equation right here, is equal to the mass of B times my speed of 6.904 meters per second squared divided by my radius, which is 0.7 meters. And I can solve for the mass. That's roughly 49 divided by 0.7, which is about 70. So MB is approximately 2/70 kilograms.
What is it?
Pardon?
Isn't mass B 0.5?
That's for that word problem that we did right there.
Oh,
But
it is for a different.
this is specifically for this,
Okay.
or roughly for this. And 2 divided by 70 is 0.03. 0.028. 1.5.
8. Or, yeah, 8.
0.285.
Yeah, there's no.
0.285, okay. Good grams. So a little under 30 grams. And as coincidence would have it, we'll be doing a lab similar to this. Couple words of warning. Whoever's doing the swinging, you'll be doing 20 revolutions instead of 10. Your arm might get tired. It is nice if you can have one person do all of it, but I understand if that doesn't happen. You want to make sure that the tape, it doesn't actually touch the bottom of the tube. Because some people have had big masses of tape here, and to the point where when it hits the tube, the tape's not going through it. And at that point, you now have, the tension at the end of the string is not the same as the tension down here. Because you've now introduced a pulling force in the middle of it. Also, I have found some people, when they swing it, you want to swing it as horizontally as possible. Some people, when they're swinging it like this. In one particular situation, I had a student who was swinging it, he could not get it straight, and I said, hey, why don't you rotate it the other way? And when he did that, it got much more horizontal. So if you're having trouble keeping it horizontal, try swinging it the other direction.